In this video, we're going to be taking a look at 3 example scenarios where we're translating some descriptions into kinematic curves. We have 3 main motion graphs, our x versus t, position versus time graph, our velocity versus time graph, and our acceleration versus time graph. Now let's go ahead and take a look at the first one. It says A is at rest for a few seconds, doesn't matter what it is, a car is at rest for a few seconds, speeds up away from the traffic light, slows down, and then continues to a complete stop. All right, now for this one we have a car going forward, so we're going to assume that is moving in the positive direction the entire time. So we want to make sure we're rising up on our graph. From there, each type of motion that we read, we want to make sure we figure out if it's going at a constant velocity or accelerating, and then if it's accelerating, whether it's speeding up or slowing down. So the first part says it's at rest for a few seconds, so we make sure we have a straight line where it's not changing position. Now, anytime it's a constant velocity, it will be some kind of straight line, but it'll be slanted, positive, negative, or completely flat. This one's at rest, so it's completely flat. Secondly, it speeds up away from the traffic light. Now, if it's speeding up, that would mean that its slope is getting increasingly steeper to show that the rate at which it's moving is greater. So from there, we're going to rise up in the graph and then make the line get a little bit steeper. Third, it says it slows down and then it comes to a stop. Okay, so now instead of getting steeper, we want to make our line get progressively more flat and then stop towards the end. So it's basically a 4-part motion. If you want to take a look at it in 4 chunks, it looks like that. Where section 1 and 4, we have a slope of 0, which means the position is remaining constant, which means it's not moving. And then for this section over here, it's getting steeper to show that it's speeding up, steeper as in getting more and more vertical in the positive direction. And then in this portion over here, it's slowing down. The slope is getting less and less steep, becoming more flat as it moves from left to right as the time elapses. Okay, so a recap for our position versus time graph. We want to figure out if we're going in the positive direction or the negative direction first. This one we're going forward in the positive direction, so we're rising up on the graph. If it's constant velocity, we want a straight line, which might be flat or slanted. If it's speeding up or slowing down or accelerating in any way, we want to make sure we curve it to get steeper if it's speeding up and more flat if it's slowing down. All right, that covers our position versus time graph. Now we want to get to our velocity versus time graph, which is representing the same motion 4 different ways. So if it's not moving, we're going to have a velocity right on the x-axis to show that it's going 0 meters per second. Now, if it's speeding up and it's getting increasingly faster in the positive direction, then we're going to show a constant positive slope to show that it is speeding up in a uniform way in the positive direction. Okay, if something's speeding up, the rule isn't to make it a positive slope, it is to slant it away from 0. And you'll see another example later on where it's slanting away from 0, but it's actually a negative slope. And then when we get to the third portion, it's slowing down. So instead of slanting away from 0, we're going to slant towards 0. And then the fourth portion, we're stopped again, so we're right at 0. Okay, if it's uniform accelerated motion, your velocity versus time graphs are going to be perfectly flat lines if it's a constant velocity, and it's going to be a straight positive or negative slope if it's accelerating, speeding up, and slowing down in some way. Now, when you go to your last graph, all you need to do is pay attention to the slopes of your velocity time graph to see the rate of change. So for the first and fourth section, there is no slope, so we have no acceleration here, no acceleration here. And then if you take a look at our speeding up section, it has a constant positive slope, so that means it has a constant positive acceleration. And then our third portion where it's slowing down, it has a constant negative slope, so it has a constant negative acceleration. All right, so that does it for our first example. Our second one, a student runs at constant velocity back towards the school, towards the origin, gets tired, runs at a slower constant velocity, and then continually slows down from getting tired. All right, so this one is going back in the negative direction. So we're going to make sure we go in the negative direction by bringing our line down on our graph. So they're moving at a constant velocity, so that means constant negative slope to show that it's going at a constant velocity, and then they get tired and they run at a slower constant velocity. Remember, the steepness of the slope is always representing the velocity of the object on a position versus time graph. So if they're slower, then their slope is getting more flat or less steep. Okay, so we'll go a little bit less steep there because their position isn't going to be changing quite as fast. And then they continue slow down from getting tired. So my last part, we want to keep on going, and then we get progressively more flat. Whoops, I'm not supposed to curl. All right, so we get progressively more flat. All right, so 2 constant velocity portions for the first and second section to show the speed is faster or slower. You make the slope steeper or more flat. The second portion is slower, so we're going to flatten out the slope just a little bit. And then for the last portion, it's continually slowing down, so it's continuing in the negative direction, but getting more and more flat as we go for section number 3. All right, now go into the velocity versus time graph. Again, anytime you take a look at the velocity versus time graph, you're thinking about the slopes or velocities from your position versus time graph. Now, we have 2 constant negative velocities. So we start with 1 constant negative velocity, and then the second one, it's not going to be a continuation of that line because it is a smaller negative. So we're going to get a little bit closer to the x-axis. Anytime you get closer to the x-axis, that's closer to 0, showing that it's slower in the negative direction. And then it says it continually slows down. So this one is going to be more gradual. If it's slowing down, remember we're slanting it towards 0. Okay, we're not looking at if it's a positive or negative slope, slanting it towards 0 for slowing down and away from 0 for speeding up. Then we take a look at the slopes of each of our segments on the velocity versus time graph. We have no slope for the first portion right on 0. And even though we're moving a little slower, we still have no slope for the second portion. We're on 0 again. And then this one has a positive rate of change, so that is a positive acceleration. Sometimes people will wonder why you have a positive acceleration but you're slowing down. Well, if you have a negative velocity but you're adding a positive number to it, it's going to bring it closer to 0, making it slow down and head towards 0, which is at rest. All right, going to our very last one. We have a dog runs forward at a constant velocity, immediately speeds up in the other direction after a ball is thrown, and then slows down to grab the ball. All right, so this one is going forward and then backwards, so we want to make sure we rise a bit and then fall to show the positive and negative velocity. So we got forward at a constant velocity, so straight line, positive direction, and then immediately speeds up in the other direction. Okay, so we want to go down on the graph, but we want to get more and more steep. Okay, so we're going to go like this and make it a little bit steeper as we go. And then it slows down to grab the ball. It's still running in the same direction, so still negative, but our slope is getting increasingly more flat as opposed to more steep. Okay, so this one we have speeding up in the negative direction and slowing down in the negative direction. So now when we go to our velocity versus time graph, we have a constant positive slope in the beginning, so we have a constant positive velocity here, and then it's speeding up in the negative direction, so it's going to be negative, slanted away from 0. Okay, like I said, when you're talking about speeding up or slowing down, we're thinking slanting away from 0 or slanting towards 0. So this is slanting away to show it's a greater and greater negative velocity, and then it's slowing down in the negative direction. So we want to stay underneath the x-axis, but then slant it towards the x-axis. Okay, so all of this is still negative, except it's greater and greater negative, and then smaller and smaller negative to show that it speeds up and slows down as it's chasing the ball in that scenario. Again, once we go to the acceleration time graph, we're just taking a look at the slopes of our velocity time graph. So we got 0 slope for the beginning, so I'll scribble one right on the 0. And then we have a constant negative slope for the middle portion, constant positive slope for the final portion. All right, so to sum things up, our position versus time graph has the most variance in their shapes because they could be straight, slanted, and curved. If they're straight, they're showing constant velocity, either in the positive or negative direction, or flat means not moving. If it's curved, that means it's accelerating, showing that its slope is changing. We want to make it get more and more steep, more and more vertical if it's getting faster, and more flat if it's slowing down. You just want to pay attention if that's going in the positive or negative direction. When we get to the velocity versus time graph, you notice all those lines are straight, some are flat and some are slanted. If they're flat, they're representing a constant velocity. If they're slanted, then you want to make sure they're above the x-axis to show if they're positive, below the x-axis to show if they're negative, and slanting away from the x-axis to show if they're speeding up, and slanting towards the x-axis to show that it's slowing down. When we get to our acceleration versus time graphs, those are the most simple one for uniform accelerated motion. They are all flat. All you have to do is take a look at your velocity versus time graph and analyze the slope to see if they are constant positive, constant negative, or 0. So I hope that was helpful to you in taking a look at 3 different descriptions and translating them into 3 different motion graphs. Thank you for watching and listening.